check. So Adrian was great, and he was able to get back like 5–10 minutes, right?
Yes, wonderful timing.
Right. So for this one, I think one main thing is how do we ask questions? Do people post on the chat or Slack or just speak? We have not figured out how to ask questions yet, right?
I think maybe for the Keynote Speaks, as the Keynote Speak is live, so probably we can ask question after the talk, and also people can post question during the talk, and maybe we relay them to Amin after he finishes his talk. And
hey, Amin. Yeah, I think that's good. Hey, Amin, how are you?
Good morning, good evening, good afternoon.
Right. We have all kinds of people. So
indeed,
people in Asia already it's midnight now.
Oh, well, for those in Asia, thank you for staying up late.
Right. So, but they are looking forward to your talk. So, what's the protocol? Do we start now, chairs? And we wait 1 or 2 minutes? At Yale, we'll wait about 2 minutes. Okay, 2 minutes. I mean, do we start or wait? You're the boss.
Oh, totally up to you all. I'm ready whenever you are. Excited to be here.
Okay, so let's get started. And it's truly my great pleasure and honor to introduce Amin Wadat, Tech Engineering Fellow and VP from Google. I do not think Amin needs really an introduction from me, but I still have to say a few words. Of course, why you don't need an introduction? Because one, a lot of people probably have already attended his SIGCOMM keynote last year when he was awarded the SIGCOMM Lifetime Achievement Award. And also why I don't need an introduction is he has made so many significant and groundbreaking contributions in computer science, in cloud, software-defined networking, data consistency, operating system, storage, and you name it. So therefore, you probably have read multiple papers already. If not, something's wrong. And I'm teaching a cloud networking class next semester. I'm finalizing the syllabus. I pick significant papers, important papers for my class. It's not seminar like reading newspapers. I pick important papers. And 1/3 papers were written by Amin. And starting from his SIGCOMM Test of Time award paper on data center topology architecture. So substantial contributions. And also I do want to say why Amin would be such a wonderful, such a dream keynote speaker for NI is because NI fundamentally should be a very broad field. And Amin now as the Vice President of System Infrastructure at Google, his team is responsible for a very broad range of topics. For compute, which includes Google Compute Engine, Borg cluster scheduling, operating systems, and kernel. And also for platforms, which includes TPUs, accelerators, servers, storage, and networking. And also for network infrastructure, which include data center, campus, RPC, and in-host net software. So basically his technical depths and also broad vision would be incredibly valuable to guide this community. Last, I do want to set a little bit expectation and put a little bit pressure on you, Amin. Amin has a long reputation of giving wonderful talks and lectures. I believe last year when David Tenenhaus was introducing you and he mentioned that there are very few things which he wanted to get up early, like 7 a.m. And listening to a talk about Amin is one of the very few. And I know Amin about 20 years ago. I think 20 years ago, I interviewed at Duke. At that time, I think Amin was still an assistant professor a long time ago. And I was able to meet several students from Duke. Even at that 20 years ago, and a lot of things students told me would be, Amin would give wonderful lectures. And whenever Amin speaks, and they are all ears. And today I'm all ears. I think we're all ears and we're listening to your guidance. Thank you, Amin.
Thank you so much for the super kind introduction, Richard. I do remember your interview well, and of course I've had the pleasure of following your work and being inspired by it myself over the years. Today I'm doing something a bit brave, perhaps, so we'll see if I can live up to the standard that you set. I'm presenting essentially all new material, which has its pros and cons. Hopefully you'll find it interesting. I certainly had fun putting it together, but there might be some rough edges, in which case I'll look forward to questions and feedback, and hopefully you all will help make this talk much better over time.
Wonderful.
Okay, so title of the talk is Application Defined Networking, and let's see what that might mean. Next slide, please. So I think one of the things, as a person who loves networking, one of the things that I worry about is that many modern applications do not actually take sufficient advantage of the network. There's just so much potential in terms of what we could do for applications and how services could be structured for, in the end, yes, much better performance, but much different capability. I see some notable exceptions to this. Machine learning training and high performance computing have long had a deep dependency on the network, and we see that actually for at least these two and a few other applications, if the network isn't super predictable, super fast, super reliable, super low latency, applications really feel it, and they know that their dependency is down the network. On the other hand, they don't necessarily want to think in terms of very low level metrics of the network. I don't think you see ML training or HPC people necessarily teams talking about things like routing or things like congestion control or thinking in terms of packets. And that'll be one of the themes and messages that I want to send here. Now, on the other extreme, probably one of the biggest trends happening across certainly industry, but I think also being picked up a lot by academia, is the move toward microservices as the way to structure distributed systems. For me, this is a really exciting opportunity, but on the other hand, it's also a bit of a concern because the way that microservices interact with the network is actually at a very coarse granularity. In other words, the coupling and ability for applications to leverage one another, microservices to leverage one another, is fairly limited and to some extent by design. So what I see in many communities is actually almost a fear of the network. The network is something to be suspicious of. And anytime that you need to take advantage of the network, you're actually taking on some risk. And that philosophy is not without merit. In other words, you are taking on some risk. So what do we do in the networking community to actually make it irresistible, if you will, for application developers to take advantage of the network? And we'll talk about that a bit here. When you see ML training in HPC, the thing they have in common is there is no option, right? Without taking advantage of the network, you don't have infrastructure services. I believe that we're getting to a place now today where the next generation of systems efficiency has to come through much deeper coordination, coupling, if you will, between computation, communication, and storage. And of course, the network's going to play a key role here. Now, one of the things that's very different in a service-oriented world is that it's going to be multi-programmed, it's going to be multi-tenant. In other words, on a given distributed computing infrastructure, we're going to have dozens, hundreds, thousands of individual services that are simultaneously multiplexed onto a shared network platform. Of note, this is typically not the case in, let's say, ML training and HPC. Right? In other words, one of the reasons that applications are more able to take care of the network, take advantage of the network, I'll say, is that they get more predictability. They can count on being able to do what they want with the network and optimize it and specialize it in the way that they need. So I don't think that we should be giving up on multi-tenancy. It's just too critical for the success of services. But then how do we provide the illusion of isolation and predictability such that we can expose the network in a meaningful way, not just from a point-to-point perspective, but in a, let's say, virtual cluster environment, multi-point to multi-point perspective. So this leads to a question in terms of systems architecture moving forward. I think there's a real opportunity for distributed runtimes that are aware of application meaningful end-to-end critical paths. What I mean by critical paths is not what you might think in terms of what is the shared bottleneck between point A and point B, but here is the higher level operation that an application is attempting to complete. That higher level operation might be a training step in ML. It might be a search request to a search engine. So the point is, how do I simultaneously compose the compute, the communication, and the storage in service of delivering substantial efficiency for that end-to-end critical path operation? And yes, that might mean better routing, but it might mean a whole bunch of other things, like, for example, load balancing, rate limiting, thread scheduling, compute scheduling and placement, and a wealth of other things. So the hypothesis behind this talk is that as data sets continue to explode, including for things like inference that is moving beyond ML training, the next frontier in efficiency is going to require application-defined networks. Okay, next slide. So just a bit of background, and to some extent this talk signals a transition from software-defined networking to application-defined networking. Of course, it's a generalization to some extent, and it really opens up a big opportunity. In other words, it's because we have the capability to leverage software-defined networking that we can move into a world of application-defined networking. So just a bit of background for the audience. I believe that software-defined networking has really set the basis for how we build underlying network systems, because we've moved away from fully decentralized networking protocols to a design philosophy that says, I can view my network as an integrated whole. It's not 1,000 or 5,000 or 10,000 switches that make up the data center network anymore. It is, in the end, hopefully from a management perspective, hopefully from the application perspective, it's a 10,000, 20,000, 40,000 port switch. Right? And it has 10,000, 20,000, 40,000 servers, perhaps storage elements connected to it. And SDN really allows you to export and manage that abstraction. It also comes with some substantial simplification and performance optimization and opportunities. So the way to look at it is that if you want to do convergence in a distributed environment with thousands of switches, you require order n log n communication steps, right, among all the switches, or order log n convergence. Now, fundamentally, if you have a centralized system, or at least a logically centralized system, you only need order n communication and constant time for convergence. Right? Like trivially, what you can imagine is that all switches, this is not how you would build it in practice, could talk to a single centralized master, right, with order n communication, and in one step, one round trip, figure out what the new converged state of the system should be. Of course, in practice, things might be less efficient than that, but we can actually approach much faster systems, but also simpler to reason about global state and global convergence. And we've gotten here because we've developed over the decades now a deep understanding of what scalable, fault-tolerant, and logically centralized services can look like, and we've really been able to apply that to networking. Next slide. So I don't want to, excuse me, I spend a lot of time on this here in this talk, but at Google, we've been able to apply the ideas of SDN to 4 of our main networks or network components. The D4 RAN, this is a private data center interconnect. Jupyter, our data center networking infrastructure. Andromeda, which is our stack for network function virtualization and overall network virtualization. Basically, this is how we allow virtual machines to be able to be multiplexed onto a shared underlying network. And then Espresso, which I'll be talking about in more detail later on in this presentation, is our software-defined networking infrastructure for peering with the public internet. Okay. Next slide. So what does it mean to go from software-defined to application-defined? I'll argue that at least in many industrial settings, and certainly from an academic perspective, software-defined networking has been a massive success. We have been able to move to centrally logical control and integrated management, and I would say that even the established networking vendors that have been long out there are adopting SDN ideas and presenting at least a centralized view of infrastructure rather than a box-centric view, a switch-centric view, or a router-centric view. And as a result, networks in practice are integer factors, right? So let's say greater than 2x, perhaps much more than 2x. More predictable, more reliable, more performant, and more cost-effective. The reliable one has been one of the more surprising and interesting ones for us, in that for a long time the debate was, can a network under centralized control meet the requisite levels of availability for infrastructure? What we found actually over the years is that while before, let's say our data center private WAN was much less reliable than our public network connectivity, through now a decade, essentially almost of time, and really I think the differentiator has been a very rapid iteration. We've actually been able to exceed the reliability of our public network connectivity in systems like before. And when I say iteration, what this really means is that, let's say on a bi-weekly basis, we can do software releases, essentially across all of production, improving the same kinds of improvements in a complete decentralized world without SDN tend to take much longer. So just from an iteration perspective, we can move more quickly and get features and functionality and improvements out there much more quickly. I would say there is one large frontier remaining for SDN, and that is the lack of open standards. And this is the problem for SDN. In other words, I would say the big hyperscalers, including Google, have their own internal implementations of SDN, but none of them would interoperate with one another. So I think that we do need to do more as a community, including companies like Google, of course, to establish some open standards. And there is some work underway here. I have one reference here on some protocols called PIN, including some open source software that will be available as part of that. Well, but based on that foundation of software-defined networking, I think that we now are in a place where we can actually integrate with the application because we have well-defined APIs, and again, this logically centralized view of the network. So there is an insertion point for applications, or this distributed runtime I was talking about that is aware of higher level application operations, can come to the network and say, this is what I need from you right now. These are the set of operations that I'm running, not the set of packets I'm sending, not the convergence time I need for my routing protocols, not what my TCP congestion control looks like, but here are the operations that I'm currently running, and here's what I need for them to run well. And then this allows the runtime to integrate into similar controllers that might be running in support of compute and storage. So for example, one could imagine being able to do job placement in a network aware manner by saying, I know that among my, let's say, 2,000 instances for my job, these 200 are really tightly coupled. They need to talk to each other at high frequency. So for these 200, I'm going to place them in a topologically aware manner, such that actually the number of hops that they have to traverse and being able to talk to one another are limited. And maybe I'm going to do it in a over-subscription aware manner, such that I know when I place these 200 jobs, I want to place them in such a way that they're not co-scheduled with other jobs that are heavily network intensive. And that means that there'll be sufficient bandwidth that I can reserve and allocate to those 200 instances. The point being that I can only do this if I'm aware of higher level application requirements. Otherwise, if I just say, well, jobs get placed randomly, they communicate however they communicate, and the network is left in a place where it has to react dynamically at nanosecond and certainly microsecond granularity to the dynamics of the application, well, it can do okay. And we have a lot of smart network researchers and of course, a lot of companies who are going after that reactive model. Hey, I'm at the whim of the application. They do what they do, and I'm going to try my best to keep up. That's one model, but I will, just as software-defined networking said, fully decentralized protocols are harder than centralized ones. What I'm arguing is, rather than being completely ignorant of what the application is doing, by inserting application intelligence into the network control plane, I can make my job much easier in supporting the needs of the application. Let me give one more example, and that would be replication and storage systems. For durability and for availability, we have to replicate. In other words, this is an underlying feature that any storage system that is going to meet the needs of applications has to have encoding. But now the question is, when I'm trying to read a piece of data, where do I go? I might have it coded across multiple replicas. I might have it available in full across 3 replicas, encoded across some others. The answer again here is, rather than thinking about routing packets, how do I know for a particular client which instance, which replica I should go to when I'm doing a read? Similarly, if I'm doing a write operation, which subset do I go to establish the quorum? I can do all of this reactively, or if I know, again, what the higher level goal is, I might actually place my replicas in such a manner that I can be aware of things like topology. For example, I probably wouldn't want to put all my replicas under the same top of rack space, just from a fault domain perspective. At the same time, I might want to have one replica close to the set of compute instances that happen to be reading it heavily. Again, for network predictability, for network provisioning, etc. So there's a very interesting set of constraint satisfaction problems that one could extract when we're thinking in terms of co-optimizing network, compute, and storage. So overall, this visibility into distributed system structure, into things like load balancing, thread scheduling, remote procedure calls, remote direct memory access, and collective operations like barriers, all reduced and related, give lots of opportunities for the network to, again, do a better job in supporting applications. Next slide, please. Okay, so as successful as SDN has been, it's still about packet delivery and connection management. And so the networking community naturally optimizes for these concepts and the metrics that are related to packet delivery and connection. Of note, if you ask an application developer, they do not care at all about packets or connections. Even the concepts, I mean, I think if you go to the most advanced application developers, they probably haven't actually encountered packets or TCP since they were maybe undergraduate. So the entry point, I would say, for most advanced developers is the remote procedure call. That is the basis for them thinking about the network. So again, perhaps obvious, but briefly, a remote procedure call involves an efficient encoding of a function and the parameters of that function to some logical endpoint. It's not to an IP address per se. It of course might resolve to an IP address, but the point is I have some service that is providing the ability to execute a function for me. That service might be replicated at multiple points in the network. Now, the instance that I go to might depend on network load, CPU load. It might even deeply, if I'm really caring about the best level performance, depend on thread and cache state. So imagine that in the limit, what I would want to happen is when I make a remote procedure call, at the moment that the set of packets that correspond to all the information needed to start that remote procedure call arrive at the remote side, I have a thread warm, ready to go, right, with no kernel scheduling delay, and L1, L2, L3 cache state ready to run that operation at peak efficiency. Now, this requires potentially a huge, potentially an unscalable amount of state that needs to be maintained in the system, but it also introduces a pretty interesting problem that without solving these sorts of problems, we actually can't get to our goals for low latency. So let me give you one example. If I decide to schedule a particular thread on a remote server to run an RPC, and that thread is on a core, CPU core, that is in a low power state, it could be maybe even milliseconds before that core can spin up to run the code effectively. Now, we on the networking side might be focusing on some amazing congestion control protocols that ensures the packets get there in 10 microseconds. On the server side, if it takes 10 milliseconds for the CPU to actually spin up and manage the request, all our work on the network side was quote unquote wasted. We might as well have taken it. Perhaps again, continuing with the obvious, a procedure call may span many packets, and potentially the work cannot begin until all packets arrive. There may be exceptions to this. And as we described in the example, the RPC latency, this is not network latency, but RPC latency from the perspective of the application developer is the time it takes for them to get the response to their function call. Right? And that can be dominated as much by end server state as network state. The end server state might be the destination server that's managing the computation, It could be actually the local server, which has the job of encoding the RPC, getting it onto the wire, and transmitting. Next slide. So from RPC, it's interesting that, again, from the perspective of the application, they often don't care about even individual RPCs. It's oftentimes collections of RPCs that matter from the application perspective. So I may have, and quite easily, hundreds, perhaps thousands of RPCs on the critical path to completing an application level operation, like search for a set of terms. And this actually winds up being a very common design pattern in distributed systems, not just for search. So you can imagine that there's a front-end coordinator that is basically attempting to run an operation across way more data than it can manage locally. Okay? So it's basically running a join operation across, let's say, hundreds, perhaps even thousands of backends. And it needs to go across these thousands of backends because the data, the index, if you will, is far too large for any single server. So I've partitioned perhaps even petabytes of data or more across many, many servers, and I need to have them each complete their portion of the request. So I'll send an RPC to hundreds of backend partitions, which will do the some local work, come up with a response, and then send the answer back. The coordinator can't actually answer the request, can actually come up with the appropriate response to the end user, let's say, until all, or certainly the vast majority of the responses have come back. So now you can imagine that, again, from the perspective of communication, from the perspective of picking among replicas. So now imagine that these partitions are not are replicated. In other words, for availability, they have to. In a system like this, we can have any server go down at any particular point in time. So this coordinator doesn't have a single endpoint to pick from when it's running these RPCs. It usually has 2 or 3, all of which have the same data available for a particular query, but the correct one may depend on what's happening across the system. You can see how trying to deliver the best performance for the application involves coordinating it across hundreds or thousands of operations that involve, yes, the network as a big component of it, but also compute and also storage. Okay, next slide. Okay. Yeah. So the ultimate illusion for a lot of this is, again, in a multi-programmed world, is how do I take my individual applications and map them to a cluster? So if I have a cluster with tens of thousands of servers, and in the end, thousands of individual applications or more, and I have general purpose compute, I have accelerators, increasingly for things like machine learning, for video encoding, for video recognition, and more. I have a flash storage pool. Perhaps I have a non-volatile RAM storage pool, and I have a DRAM pool. How do I then do the placement of my storage, the placement of my compute, and set the connectivity for my network such that each of my applications have a view of dedicated infrastructure, right? A dedicated composition of networking, of compute and storage for their service, just as they might for ML training or for high performance computing, so that they can effectively coordinate, they can have their runtime coordinate for their individual operations to maximize their performance. Again, one of the hypotheses behind this work is that these distributed services can become integer factors more effective, more efficient, operate over integer factors more data in sort of the real-time critical path by being able to coordinate across the different systems that make up the different pieces of infrastructure that make up the end-to-end system. Okay, so how do you deliver the right level of predictability? How do you ensure that you do so in a multi-tenant world? And what I'll say is that, again, if you have to program defensively, you're going to really hurt your opportunity for optimization and for efficiency. Today, even in data center network settings, you have to assume that an RPC takes at least a millisecond. And this is for a RPC that basically there's no computation method. That's your baseline. And that's because there's so much variability in the system that it's not unreasonable for an RPC to take a millisecond or more. And it's not unreasonable to think that the maximum number of RPCs that a server can do is 1,000 per second. Now, many of you might say, hey, I've read papers where the answer is 100,000, 500,000. 1 million RPCs per second per core. And I would say that there are enough simplifying assumptions made in those cases where they actually don't translate to application efficiency, nor would they translate to application uptake. So as I'll talk about a bit later, but starting here, I think that we in the networking community need to be really cognizant of application performance metrics, APM. And in the end, if we say, hey, we can do 100,000 RPCs per second, that's fine per core, let's say, or 1 million RPCs per second per core. That's great. And that's, of course, a concrete thing to be able to publish and be able to communicate. On the other hand, I think we should be interested in saying, and here are the set of applications that benefit from leveraging this RPC packet, or leverage, or that benefit from this new congestion control protocol, or who benefit from this new routing convergence system approach. Next slide. So let me give a couple of examples. I'll keep them short. One is actually taken from our SIGCOMM 2017 paper on how we integrated SDN into our edge routing infrastructure. Lots of details in the paper, but I think that this is a good example of the kinds of things that can be done when you're integrating networking with the application level. Okay, so next slide. Okay, so essentially what we did was before Espresso, we had router-centric protocol. Right? We had routers, big boxes that operated on a local view that focused on connectivity as the basis for optimization. In other words, making sure that there was some path between source and destination, and that performed a rather coarse fault recovery. With Espresso and moving to software-defined network-based steering, we were able to take per metro and global view. In other words, it wasn't what was happening at a single box, the single router that we cared about. We could look certainly fairly easily at what might be happening in, let's say, all of Frankfurt or all of Chicago, or pick your favorite peering point. We could leverage application signals, and we could perform real-time optimization, not based just on delivering connectivity between source and destination, but based on delivering the best performance. So the observation here is that the path that you take on the internet between a source and a destination can dramatically influence the performance and stability of the higher level applications that are taking advantage of that path. So for us, one of the most demanding services that we host at Google is video. So in trying to deliver a smooth video experience to users across the planet, what we found is that the actual peer that we pick for a particular session with a particular user dramatically impacts the user experience, and that we can't make a static decision. So in other words, over the course of the day, based on real-time conditions at an ISP and real-time failures that might be taking place on the internet between us and the destination, can really impact how good an experience users are listening. Okay, so let's dive into this a little bit. Next slide. Okay, so here's a picture of a Espresso Metro, and at this point, essentially all of our metros, and we have let's say hundreds of them across the planet, are running our Espresso SDN stack. Look like the following: we have our peering traffic set of switches that we deploy, and a set of servers that we deploy in our peering metros, and we have BGP speakers. Now, these BGP speakers are essentially, you can think of them as running on servers. They don't have to be running on a particular switch or on a particular router. They will communicate and establish BGP sessions, which is of course the lingua franca for the internet, with external peers. And at a particular large metro, it could be dozens, perhaps even hundreds of peers that we're connecting to that are peering traffic. Next slide. So the interesting thing that we do here is that all of our hosts, so we also have, you can think of them as layer 4, layer 7 proxies that terminate user requests at these metros. We do this for high levels of availability and predictable performance. Regardless, this was true of our infrastructure. We have these front ends at metros. It's true of many cloud service providers and CDNs where the connections are TCP terminated at the edge. There might be, of course, and often are connections back to data centers in the core. but the stream in the end will come from these servers that are located on the edge of the network. Now, the host runs our own packet processor. So we have been able to insert into each of our hosts the user space stack. We've actually since published the details of that as well, but it is a high-speed packet processor that allows the host to insert a label onto each packet, and the label specifies which external peer that a packet should go to. And this label is determined in near real time based on a processing system that keeps track of actual delivered performance to users across the internet. So we'll see this in a second. Next slide. Okay, so the idea here with our SDN stack is that we have a local controller that can interact with the BGP speakers, and it can also interact with the host and the packet processor that's available on each host. Imagine that these hosts are sending data, perhaps video stream, to users across the planet. Now, these hosts can keep track of the delivered performance to a particular endpoint. It could be on a subnet base. So now I can build up some data based on these application signals and feed them to a global controller that is keeping track of the performance that actual clients across the internet see when you pick a particular peer at that metro to send the data to. We benefit from having a large number of clients spread across the world, so we can also actually run small experiments to see by changing our selection of egress points, how well does a peer do with the new connectivity. As we build up the state, we can then have this global controller that is, again, replicated and running multiple places across our infrastructure, inform the local controllers as to how they should be reconfiguring connections in terms of chosen external peering point for a particular subnet. So when a new client comes in and says, okay, I would like to start, let's say, a video session, I now know where I'm going to send that client request by essentially establishing the TCP connection back to the right host that can then also, through the label switch fabric, with the appropriate forwarding table entry, determine how to send the packet to the right next hop here so that the best end-to-end performance and availability in the end will be delivered to the client. Next slide. So one of the things that early on in SDN we focused on, and that was super meaningful in the context of things like data center networking and our V4 WAN, was the cost of the infrastructure. Here, though, actually, I think the important goal was not the cost of the infrastructure, because we actually were most worried about application performance and really being able to improve the user experience. So with Espresso, we focused on a couple of things, which is the good put, basically the video rate that is achieved to the client. So this is not a low-level metric of sort of packet rate, but it's the actual good put delivered to end users. And then even more important than good put is a metric that we track called mean time between rebuffers. So essentially, this is the expected amount of time that is going to pass in a video stream before the user gets the spinning circle that says, oh, I don't have enough bandwidth for me to continue playing this video stream in real time. And across three major client ISPs, anonymized A, B, and C, what we saw was that the mean time to rebuffer improved substantially across all of them, going from, let's say, 10 minutes to 20 minutes. So factor 2, factor 3, factor of, let's say, 50%, 40% or so, while the bandwidth also substantially improved, somewhere between 33%, good put in this case, of the video streams, improved by 33% to a factor of 2. The important thing to note about the good put is that actually the client will adapt their encoding rate and the quality, let's say going from standard rate to 480p to 720 to 1080 or 4K, depending on what's available. So not only were we able to deliver substantial improvements in the connectivity, meaning the mean time to rebuffer went up, but simultaneously we were able to deliver higher quality video streams, as noted by the good put improvement that resulted. So the goal here was to really focus on the application performance metrics, not the lower level metrics from a network centric view. Be able to take real-time signals of what's happening across the internet and feed that back into the network controllers to say, here's how you should forward packets, here's how you should route, here's how you should leverage your peering protocols to deliver the best quality of experience to the user. Okay, next slide. Okay, so for time, I'm going to go through the second vignette somewhat quickly. We've also taken some of this work in really focusing on the application level per RPCs. As I mentioned, RPCs is the basis for how applications think about the network, not packets. Let's see some of the details here. Next slide. Okay, so one of the key observations here was that actually we found that lower level networking metrics, for example, round trip time and bandwidth, do not sufficiently capture the performance of applications. So what we measured how much better application performance metrics we could deliver just by reducing network RTPs and improving network bandwidth. And it turned out that the correlation was modest to weak, not as high as we'd like. Also of importance is that over 95% of our internal traffic is actually remote procedure call. So this is a great entry point for us to think about how we can make the application experience better. Okay, next slide. One of the things that's happening, at least at Google, is that what we found is that the network latency tail did correspond to the RPC latency tail. So what this graph shows is that what happens when a service basically undergoes a big spike in load. So you see the blue line capturing the load of a service, varying from, let's say, normalized at 1x, but jumping in this graph instance to 4x. The y 20x, the right-hand axis shows the latency of RPC between 1x and 4x. What we see is that when the service undergoes a spike in load, the RPC, their latency also goes up substantially, and that there is some correspondence with the network latency tail, but not as strong as what we'd like. So we really want to focus on the RPC latency tail, which sees substantially, let's say, bigger increase when the network and the service overall is seeing a spike in load. Okay, next slide. So the notion here is, and just to make progress, even though in the end we do need to and want to bring in the end compute stack, scheduling, etc., we focused on network RPC latency. And while I won't go through the details here, I think it's important to note that there's lots happening on the end host in terms of even just RPC. Right? When we have an RPC request, we do segment it up. We do the RPC stack. We go through transport, wind up a packet. We go through the NIC, which might also be doing processing of the packets, etc. The packets go across the network to the server, and then the acknowledgement and the response from the RPC similarly goes through the reverse path. So if you want to stop even at before the compute run, there's a lot of components that have to get involved on the networking side, from the end host to the network and back, when we're talking about RPC latency. Next slide. So again, going through this too quickly, what we found is that the RPC network latency depends both on bandwidth and the RTP. When we just focus on one metric or the other, it's not enough for us to capture RPC network latency. So the point is that actually you care about the metric that's more meaningful to the application, and you can't necessarily focus on a single metric of the network to be able to optimize. Similarly, as the next slide will show.
The next one?
Yeah, next slide, please. Applications have RPCs of varying priority classes, and this is actually key, and the one that, again, the network typically doesn't have a good way of dealing with. So applications are running lots of RPCs. Some of them are for maintenance, and some of them are on the critical path for a, let's say, latency-sensitive user request. The network typically has no way of being able to differentiate between them. So I might have, again, latency-sensitive RPCs. I might have throughput-intensive ones, or I just might have best effort ones that, frankly, can don't have a tight deadline. Next slide. But what we found is that whenever basically end users were having performance problems and they thought the network might be at fault, the quick fix that they would put into place is request to run their RPCs at the higher priority level. And in the end, what they would do is they would run all or at least many of the RPCs at higher priority levels. So for example, you could imagine that a service like search is very important to Google. And we wound up in a place where, of course, we want to prioritize search traffic, but then we would uniformly prioritize all search traffic. And perhaps true, perhaps not, but you could imagine that the dynamic plays out in such a way that, for example, what you see here is that even among best effort RPCs, 70% of them, 71.1%, if you look at the right-hand pie chart, were in the QoS high class. And very, very few of them were in the QoS low class. Similarly for the latency sensitive ones, we had a somewhat strange mix between QoS high and QoS medium. The point here is that we do have this mechanism for saying these are the packets that are important to me by marking their QoS, but then making sure that the packet labeling is meaningful to the end application, and then application's RPC semantics is not something that has been done in a sort of comprehensive manner in the past. Next slide. Okay, and so the interesting thing is that over a 2-year period, what we saw is a race to the top. And what we mean here by that is that the number of low QoS RPC packets went down by 12%, whereas the medium and high QoS packets went up by 6% or 12% total. So you could imagine that essentially over time, as individual applications wind up with some performance issue, they would say, hey, I need to be in QoS medium or QoS high, so let me move there. And well, they would. And that meant that actually, in the end, everybody would be special, which meant that no one would be special. And everyone on the path that we were on would be running in QoS high. Next slide. So for time, one of the things that you could imagine doing is saying, well, small RPCs are likely to be latency sensitive ones or higher priority, and longer RPCs can be lower priority. Won't go through the graphs here, but basically our measurements show that this was not the case. You could not use size as a predictor of your RPC priority, and you actually have to look at the individual RPCs rather than try to do prioritization based on the size. Next slide. Okay, so what have we been doing on it? And this is, by the way, a work in progress, I should mention, not published yet, but underway. Essentially, what we're able to do here is mathematically know how much traffic of a particular QoS class we could admit into the network while managing target SLIs for packet delivery. And the idea here is that the application could also specify which of its RPCs were of a particular priority level. So now you can imagine, and I won't go through the details here, what the RPC stack in coordination with the transport stack can do is basically allow the application to say, for my highest priority RPC, I'm going to be able to take as many of those as possible and make sure that they run the QoS high class. And the next step might run QoS medium, and the next step might run QoS low. So the point here is that, again, by having the network integrated into the application and leveraging application semantics, we can ensure that the network can also say, hey, this is the maximum amount of traffic that you can put into QoS high. And I'm going to configure the weights in my switches or my forwarding rules, etc., in a particular way such that I'm going to be able to guarantee you this amount of bandwidth. But you can't put more than that amount of traffic into QoS high for me to be able to guarantee that. And I can work at the transport level, at the RPC level to ensure that. Next slide. So the point here is that we can control an application meaningful metric like RPC network latency by controlling the amount of traffic that's admitted on a given QoS class. And from the application's perspective, they are not thinking about actually QoS. They don't know that QoS high, QoS medium, QoS low exists even. Rather, what they know is that they want certain of their RPCs to be in the latency sensitive class, and they want to have SLOs, service level objectives, for how quickly those RPCs complete. And as long as they don't put more than some specified amount let's say, high priority RPCs into the network, corresponding to some total bandwidth in the end, and they will be able to meet the SLA. If they go over that, well, then we're going to need some further adjudication. But the point here is that we can be much more principled about what works and what doesn't work, how aggressive the application developer can be or not, and not be thinking in terms of lower level per packet QoS marking. Next slide. Okay, and so the conclusions, I believe modern applications actually do not take sufficient advantage of the network, and that there's actually huge opportunities in building much more capable applications. And by capability, I mean actually able to do much more compute per unit time and access more data for doing that compute in real time than they do today. And actually, for us to get to the next wave of system efficiency, we're going to have to drive coordination across the network, across compute, and across storage to make this happen. And this provides an interesting opportunity for distributed runtimes that are aware of the end-to-end critical path. I gave a couple of initial examples. There are many, many more here with Espresso, how we were able to take advantage of the fact that we knew we're trying to deliver real-time video to clients across the world. And we could actually, again, have a runtime that's measured and reacted to, sensed and actuated, the real-time characteristics of the network and picking peering point. Similarly, we could know the rate at which packets in the end of different QoS levels are being injected into the network, and then map that back to RPC rates to make sure that applications are getting the SLOs, the service level objectives they need for their RPC at varying priority levels, rather than thinking in terms of marking packets. So overall, what I'd love to see us all working together on is how do we start with application performance metrics and work our way down, rather than start with, let's say, per packet network specific performance metrics and work our way up. I'd love to see us say, here is a set of, let's say, sample applications. Here are their metrics, and here's how research and optimization of the network helps with the application metrics, as opposed to the lower level network metrics. Okay, with that, let me pause, and I'd love to take any questions.
That's wonderful. Thank you so much. And we are actually very tight on time, but I do think like we should give people time to ask, like, let's say 2 or 3 questions. Okay, who wants to ask question first? Rachel, you want to speak up? There's one question on the chat. Okay. I mean, do you prefer to read, or you can just answer it directly already?
When I read it to folks, how do you solve heterogeneous RPC sizes? How do developers specify those? Yeah, that's a great question, and I think that this is a open question here. I think that it really can be partially reactive, but I think that you do wind up having some distribution to the RPC sizes. It might be widely variable, but in general, it's not going to vary by a huge amount. Oftentimes, the application will know the RPC size ahead of time and can actually tell the network in one manner or another. But it is absolutely the case that in other cases might not be true. And in yet other cases, it might be an infinite size stream that happens to be chunked up as RPC. So I think that this is a good research question in terms of making sure that we're able to tell the network, but also the compute layers on the other side, what the sizes of the RPCs are. And perhaps as interesting, how much work might be required in terms of compute or data access on the remote side to fulfill a particular RPC.
So, I mean, next question, how applications, you can read it. How applications signal QoS requirements to the network? I guess, okay, go ahead.
Yeah, so it's a good question. And again, I think this is also developing, but I think the point here is to label RPCs as one starting point and label those as high, medium, and low priority. The way that we've gone after it with Akitas, sort of initial work in this space, is that we will negotiate with the network over a budget, basically an amount of, let's say, high priority RPCs. An amount might be in terms of bandwidth to begin with, to get around some of the issues in terms of RPC sizes. But as long as we stay within that spec, we can know that at least the network component of the RPC will stay within some spec as well.
Next question from Nick. Defensive programming efficiency.
Yeah, so I think that the point here is a really, really good one. Defensive programming is necessary because otherwise the application would fall over. And I think that the system is overall sufficiently unstable with sufficient numbers of failures that you have to be defensive. I think the point here, though, is let me put it this way: how would the defensiveness be dynamic? So in other words, if we're being defensive because of, let's say, server failure patterns, we might take one approach. If we're being defensive because of network dynamics, we might take another approach. But overall, I think that what we see is that many people pick constants for their level of defensiveness, hard code them based on sort of trial and error to see what works in production and what works in practice, and then live with those essentially forever. So one way to look at it is we absolutely need to be defensive. Otherwise, the application won't work. But how would we tune it to, if you will, maximum aggression while maintaining your availability and performance targets?
So next question, and integrate RPC latency into job placement? Go ahead.
No, we have not. I think it's a important direction. So one could imagine that actually you don't need to leverage QoS latency, network QoS as much, for example, if the two endpoints are on the same top of rack switch. Why? Because of the chance that you're going to have sort of bandwidth hotspotting for two servers on the same top of rack switch is much lower than if you were remote. So I think that's an interesting direction as well.
Next one, I guess he's asking which example you really use. I think probably next question.
Yeah, so what application, this is our storage system. So I mentioned 95% of our traffic is RPCs, and most of our studies is done with D, which is a block level storage system at Google. And that makes up, let's say, the majority of those RPCs. So this is based on a substantial amount of data, is the way I put it.
So I'm going to just ask one question and just jump in, and then probably this last question would be, just look at the current slides. And there are two things I take away. Number one is clearly you are talking about is one thing really struck me as loud is eventually I think the state of an overall system should be not only traditional network state, you also talk about application state, for example, what's the even L1 cache state and so on. So a lot of states you need to collect. And then you also talk about the runtime control. So what do we envision? Do you think eventually a very big framework, like analogy like ICN, logically centralized control and collect huge amount of generic state control protocols would emerge? And then you have the logical centralized control distributed. So can you give us a little bit some flavor of what you think eventually can emerge? Still a piece by wise or eventually some big unifying protocol can eventually emerge?
Yeah, great question. I don't know what the protocols are going to look like moving forward. And I would say that before we speculate too much on the protocols, I think we should speculate on and actually implement based on the state that we need to collect. Now, we're not going to be able to build a system that tries to keep track of the L1 cache occupancy among 20,000 servers and feed that into RPC stack. No illusion that we will be able to. So one can imagine that some amount of hierarchy is going to be involved, some amount of locality is going to have to be involved. I mean, trivially, what you could imagine is a first layer load balancing decision that says what server should I go to, and then once I get to the server, I figure out which thread I go to, etc. So this is not going to be centralized, and it's not going to be a single runtime that tries to make decisions for every flow or every RPC. The question is, how can I partition the needed state and needed sort of control loop in a way that I can come up with hopefully decent approximation to some of these tough answers. But I think the great thing here is actually because we're doing almost no coordination right now, some relatively simple systems can deliver incremental benefit toward a sort of a larger goal. But it's a good question in terms of what the protocols will look like and how they'll emerge. I don't feel that at least I understand it well enough to be able to give a great answer quite yet.
Right, system building, that's great. So we're almost 1 hour. I think we get into the next session, and it's truly always a wonderful opportunity. And so, I mean, just in case they have other questions, probably should send an email to you, right? I don't think you're going to monitor the channel for long, so therefore probably they have continue, and they should just send an email to you to continue the discussion.
Yeah, I'll try to stay on for a bit, but otherwise, please do send me email. I'm happy to try to answer questions offline.
Wonderful, wonderful. Thank you so much again. I mean,
thank you. This was fun. Appreciate it.
Thank you.